All right, guys, time to start another chapter, okay? And we're going to be looking at taking essentially that charge stored in a capacitor, which is static, and moving it through wires in a circuit. So we're going to move to flowing charge or moving charge. So once we have energy in a capacitor, we want to access it, okay? Now the electric field is going to be our agent of our force, okay, to move charge particles through a circuit. Now, what we're going to be talking about then is discharging a capacitor, which is eliminating the charge separation. When you connect the two pieces, or the two plates of a parallel plate by a piece of wire, what happens is the charge is redistributed, so that there will end up being no net charge on the capacitor. So I connect it with the wire. We're going to get essentially negative to flow toward the positive until we get no net charge on either side. And this happens very, very, very quickly, okay? Now, as we're exploring discharging a capacitor, we want to know, one, what causes the flow of the charge, what is the charged particle that's moving, and how fast does it happen and why, and what controls the charge flow. So, let's think about attaching a wire to the two plates, but leaving a little gap between the ends. Okay, wires are conductors, so when I connect them to the plates, then the charge redistributes over the whole surface now of the wire as well as the capacitor. There's a gap, so there is an electrical potential in the gap, right? There's charge separation. If I'm at a point here, 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 or here, the electrical potential inside the conductor is 0. Now, if we were to fill this empty space, okay, connect it up. What I have, for the instant that I do that, a conductor that's not in electrostatic equilibrium, because there's net negative charge over here and net positive charge over here. So in this region of space, there's an electric field, E. Okay? Now, that means that in that gap, there would be a net electric force on the charged particles in that piece of metal. And that means that charge is going to flow and respond to that electric field. Now, we know that the charge gradient, okay, positive to negative, and this is kind of drawn opposite the way the plates were, we're going to have a charge gradient. Now, because of that charge gradient, notice higher positive charge, less positive charge, negative charge, greater negative charge. The net electric field is going to point from higher positive charge to higher negative charge. Okay? And that's going to push, all of a sudden, all of the electrons inside the wire. So once I connect that little section up, there's going to be electric field inside the wire created essentially almost instantaneously the moment the gap is filled. Okay? So since there is going to be a charge gradient, there is going to be an electric field. The electric field is going to push things along. Now, our charge carrier in that wire is the electron. So if the electric field inside the wire points from positive plate to negative plate, the electron is going to move from negative plate to positive plate. So the electron moves in the opposite direction of the electric field vector. Okay? Now, the electrons don't have a real clear pathway. They are nuclei of atoms in there that they're dodging around. There are other electrons they're dodging around. And before anything happened, the electrons were already in motion. It was a random motion. But now with that electric field, they're getting a force in one direction. They kind of get pushed along. Now, because of that, okay, thinking about pushing the electrons dodging the nuclei, dodging other electrons, there's going to be friction. Okay? So the push from the electric field, opposite the direction of the electric field, the friction is going to point in the direction of the electric field. Okay? Friction works against it. That's why the wire heats up. Because of collisions with atoms, with other pushbacks from other electrons, a steady push is needed to move the electron C, the electron C at a steady speed because there's friction. Now, electrons have what's called a drift speed, which is the average forward speed of an electron if you were to push on them with the presence of an electric field. Drift speed is quite small. Okay? Little I sub e, the electron current, is equal to N sub E divided by delta T. It's the number of electrons that pass through a cross-sectional area per unit time. N is the electron density per meter cubed. So we could say that I sub E is equal to M little n times the cross-sectional area times the velocity. Now, I'm not going to worry about calculating that. It's really not that necessary for what we're doing. Now, if we look at stop and think problem here, 3, we want to figure out where the electric field is the greatest, so where we're going to have the greatest push. Well, since the charge on these two little kind of sections of the wire are the same, the electric field in here is 0, there is no push. Here's a +2 and a -2. I got an electric field here. Here's a +4 and a -4, no electric field. A +4 +4, no electric field. +4 -4. Now this electric field is going to be larger than this one. And here's a +4 and a +2. So this is going to be our largest electric field. This would be our next largest electric field. This would have an electric field because there's a gradient, +4 and +2. And then C and A, no electric field. Okay? Now, stands to reason the stronger electric field, the stronger the current is going to be, i.e. the larger the current, because the net force is going to be greater. So the electric flow, the electron flow, is directly proportional to E, the strength of the electric field. And the strength of the electric field is going to depend on the capacitor. At the moment the wire is connected, the electric field exists at all points inside the wire because there is an charge gradient. And you start moving the electrons everywhere in that wire at the same moment. Think about flipping a light switch. Okay? And the electrons are going to move from the negative plate to the positive plate. Each individual electron doesn't move that far. Think about water moving through a hose. Okay? So electrons don't actually have to go all the way from the negative plate to the positive plate to discharge. They have to just go into the wire, and think about them forcing electrons out the other end of the wire until we get the charge transferred. When you're discharging a capacitor by connecting it with a wire, it discharges almost instantaneously. Now, we know that electrons are the real charge carrier in the wire, but we know that people like positives better than negatives, and the stuff about current was worked out before we knew what the charge carrier was. So current I is defined as delta Q over delta T, where Q is thought of as positive charge, and the unit for current is the ampere, or quite often we just call it the amp for short. The direction of current flow is in the direction that a positive charge would move, which is opposite direction that the electron would flow. Okay? I always points in the same direction as the electric field vector, and it points inside the wire from the positive plate to the negative plate, same direction as the electric field, even though we know electrons are actually moving from the negative to the positive. Now, meet a law, the law of conservation of current. It says that the current at all points in a current carrying wire is the same. So light bulbs placed in a circuit don't use up current. Okay? It's kind of, think about the current as like water going through a water wheel. Okay? We can grab energy from the water turning a water wheel, but we don't use up the water. Okay? It doesn't slow down the flow of the water. So what we do is we're continuously pushing on the electrons with the electric field, which gives them kinetic energy, and we pull that kinetic energy out and use it to light up the light bulb. We convert it into electricity, but we're continuing to push, so we're continuing to put things in. Okay? So if I were to look at a point here, or a point here in this circuit, they would all have the same current. So if you think about it, since the electrons are continuously being pushed by the electric field, they want to increase their kinetic energy. But the light bulb, okay, slurps some of that kinetic energy up, okay, and transfers it out as a form of light and heat, and as long as you're continuously pushing, then the electron speed remains constant. Okay? So the law of conservation of current says that the current at all points in a current carrying wire are the same. Now, we met Kirchhoff's loop rule earlier. Now we're going to make Kirchhoff's junction rule. Current into a junction where branching occurs equals the current going out of the junction. So current in has to equal current out. So if this was 3 amps going in and this was 2 amps going out, there would be 1 amp over here. So let's look at this, stop and think. It says, what's the current in this wire? Well, I have 3 coming in, 4 coming in, that's 7 coming in, and I have 6 going out and 2 going out, so I have 8 going out. So if I have 7 in and 8 out, that means I have to have 1 in. Okay? So this is 1 amp in. Now, not material is a good conductor. Every material has its own natural conductivity, its ability to let current to flow. Conductors like metals have good conductivities. Something like a piece of paper has a poor conductivity. The inverse of conductivity is resistivity. The resistance of material to the flow of current. Okay? Resistance, R, is resistivity times length divided by area. So if you think about making a current flow, and you're thinking about the resistance of current flow, you want something that's got a low resistivity, and notice the length, if you're thinking about a wire, longer wires have more resistance, and if you have a smaller cross-sectional area, you have more resistance. A larger cross-sectional area, you have less resistance. It just makes good sense. You're essentially using a wire as an electron hose. And if the area is really small, you can't pass as much through per unit time. Now, let's think about resistance, electrical potential, voltage, and current. And this brings us to Ohm's law. R, the resistance, is equal to delta V over I. Or more commonly, you see delta V is equal to IR. The change in electrical potential is equal to current times resistance. Okay? The units for resistance is the ohm. An ohm is, voltage divided by current, so volts over amps equals an ohm. Ohmic materials show a linear relationship between current and applied electrical potential. Non-ohmic materials do not. Diodes, non-ohmic materials. Okay? So, in an ohmic material, as you increase the electrical potential across it, okay, the current goes up. Resistance equals 1 over the slope. Okay? In a non-ohmic material, like a diode, okay, increased potential, no current flows, and then all of a sudden, current takes off. And notice that's not a linear relationship. Okay? Diodes then can be on-off switches. Under certain voltage conditions, no current flows. Under other voltage conditions, you get high current flow. Now, let's think about current and batteries and circuits. Okay? A battery, okay, can be a source of electrical potential and electric fields. A capacitor can also be a source of a current and an electrical potential and an electric field. It's just that in a battery, because you're using a chemical reaction to maintain charge separation, you can maintain the strength of the electric field and the electrical potential and the current for an extended period of time. A capacitor would deliver a variable electric field and a variable current over a very short period of time. So batteries are a better way to long-term deliver current. So we're going to concentrate mainly in on batteries as our source of electrical potential and current. And a battery is what we call a DC component. DC stands for direct current, which means the direction of the current flow is always going to be from the positive terminal to the negative terminal. Electrons flow in the opposite direction. Okay? Now, the electrical potential created by a battery is going to be equal to delta V divided by L, where L is the length. So if I have a wire, the longer the wire, okay, the weaker the electric field is going to be. And current is equal to delta V divided by R, the resistance. Now, we want to control current flow in circuits. And we can do that by using devices called resistors. These are devices where we control the resistivity, and that way we can control the rate of current flow. Okay, so a resistor is a device built to restrict the flow of current. An ideal wire for us right now is going to have a resistivity of 0. Now, in the real world, we know that wires have resistance. But, you know, we're playing physics fantasy land, so an ideal wire has no resistance. An insulator has a resistance of infinity. Okay? So let's stop and look at 30.6. Well, we're going to look at this situation here. Okay? Now, let's move this down just a little. Here I have 3 identical wires, and they're both, this wire is hooked up to this battery. These 2 wires are hooked up to this battery. Both of them have the same electrical potential. So if I looked at point A and point B, because they're in the same wire, with the same electrical potential over the wire, okay, our conservation of current says that those 2 have to have the same current. Current is everywhere the same in a single wire. Now if I look at C and D, they're in 2 different wires, but they're wires of the same length and they have the same potential across them. So it turns out that the current flow at point C and point D are also the same. And since those 2 batteries are the same size, A, B, C, and D all have the same current. Okay? Now, that ends the chapter. And we are ready for chapter 28. Chapter 27 was really short. Okay? So let's scroll on up. Chapter 28. Okay. Now, we're still dealing with batteries as our voltage source. So we're dealing with DC power and a DC current, a direct current, which means the wire is always going to flow in one direction. AC is when the current changes direction with time. Okay? AC power is what you have in your house. DC is what you get from a battery. We'll talk about why we use AC for houses later, okay? But right now we're going to stick with DC because it's a little bit easier for us to work with mathematically. Now, as we look at circuits, we're going to start using symbols to represent things. A battery is represented by parallel lines, long lines, short lines. The longer line represents the positive side, the shorter line represents the negative side. A wire is just a straight line. A resistor is a jagged line. A light bulb is a circle with a loop in it. A junction, okay, just lines coming together. A capacitor, the parallel lines are equal in length. And a switch, okay, and this would be an open switch. Sometimes you'll see little arrows drawn here to say the switch is closed. Okay, now here's some representations of circuits. Okay, so I've got a battery, capacitor, and a resistor, and they're connected. Now, what I want to do is I want to figure out which one of these circuits is the same. And which one's not like the other. Okay? Now, if I look at A and B, I have a battery that's in parallel with a capacitor and parallel with the resistor. And the resistor and the capacitor are parallel. Believe it or not, A and B are exactly the same thing. Because I've got a battery in parallel with this resistor and parallel with the capacitor. If I look here, I've got a battery in series with a resistor, okay, to the junction, and then I've got the capacitor. This one's not like A and B. Let's look at D. I've got a battery in parallel with the resistor and then parallel with the capacitor. So A, B, and D are actually the same. C is the odd man out here. Okay, now look at it. If you think about it, I can go around here and back and around here and back. Okay, here I can go around here and back, around there and back. So I can go through the resistor without going through the capacitor. But here, I have to go through the resistor and back. To get the capacitor, I have to go through the resistor. Okay? Now, with basic circuit analysis, we can determine the potential difference across each circuit component and the current through each circuit component. To do this, we use Ohm's law, Kirchhoff's loop rule, and the junction rule. Okay? So you can look at the tactic box on page 893. So let's get to the tactic box. It's on page 768 now. It says draw a circuit, label all the knowns and unknown quantities, draw and label a current arrow to show your choice of current flow. You could be wrong, but that's okay, the math will tell you. If you know the actual current direction, choose that direction. If you don't know the actual direction, make a choice. All that will happen if you choose the wrong way is your current will end up being negative instead of positive, which says you drew it in the wrong direction. Okay? Travel around the loop. Start at any point in the circuit, then go all the way around the loop in the direction you assign the current. As you go through each circuit component, delta V is interpreted to mean V downstream minus V upstream. So when I go through a battery from negative side to positive side, delta V is positive. If we were to go through a battery in the negative, from positive to negative, we have delta V being negative. And if we go from the one side of the resistor to the other side of the resistor in the direction of current flow, we have a potential drop of minus IR. And if we apply the loop rule, going all the way around the loop, delta V is 0. Come on. Okay. All right, let's start with a single resistor and a single battery. Okay? All right, so now let's make this a 9-volt battery, and let's make this a 10 ohm resistor. So if I started at a point here, okay, and I move around the circle. So I take my current flow around this direction, I. So the first thing I move through is that 9-volt battery. So as I move from here to here, okay, I have a plus 9 volts. If I move from, going on around, I hit that resistor, I'm going to have a minus IR. And they all have to sum up to be 0. So I have 9 volts minus I times 10 ohms has to equal 0. So I have 9 volts is equal to I times 10 ohms. So I have I as being 9 divided by 10, or I is equal to 0.9 amps. Okay? Now, let's just up it a little bit. Okay, I've got a 10 ohm and a 10 ohm, and I've got a 12 volt battery. Okay? If I start right here and I move in this direction, I'm choosing my current to flow in this direction because this is the positive side of the battery and that's the negative side. So I have 3 components in this circuit, the 12 volt and then 2 10 ohm batteries. So if I start looking at the sum of the voltages, okay, I'm going to have plus 12 volts plus a minus I times 10 ohms plus a minus I times 10 ohms, and that all has to add up to be 0. So I have 12 volts minus 20 ohms times I is equal to 0. So I is going to be 12 volts divided by 20 ohms. So 12 divided by 20 is a 0.60 amps. Okay, and I have it drawn in the right direction. So pretty straightforward. Now, let's think about doing 2 batteries and 2 resistors. Well, no, you guys can do that. That's pretty, well, no, let's do an example. So, let's make this a 9 volt. And I'll make this a 100 ohm resistor. I'll make this another 9 volt. And we'll make this a 50 ohm resistor. So if I start here and I travel this direction, direction of my current flow. Well, negative side to positive side, I have 9 volts plus a minus I times 100 ohms plus 9 volts plus a minus I times 50 ohms has to add up to be 0. So I have 18 volts minus 150 ohms times I equals 0. Solving this for I get 18 divided by 150. I get 0.12 amps. Not too bad, right? Erase all. Now, let's talk about power here for a second. Power is the rate at which energy is delivered, or the rate at which energy is used up, quote unquote. It's essentially converted from one form to another. Power is equal to current times the EMF, or the potential of the battery. So power can also be thought of as I squared R, the amount of energy being dissipated by a resistor, or I delta V R, the electrical potential drop over the battery squared, or the electrical potential over the battery squared divided by R. So there's 3 different ways you can calculate power. Now, power is the rate of energy delivery, so it's going to be in units of joules per second. 1 kilowatt is 1,000 joules per second. Now, a kilowatt hour is the power in kilowatts times a change of time in hours. It's a weird unit, but that's what a kilowatt hour is. And that's how they measure how much power your house uses. Now, let's look at problem 7. At the end of the chapter. Okay, if we look at problem 7 here, it says, what is the resistance of a 1500 watt, 120 volt hair dryer? So delta V is 120 volts, and our wattage is 1500 watts. And our rate of our power is 1500 watts. Okay, so let's look back at our equations. So our wattage is 1500 watts. So I have 1500 watts, and that is equal to I times delta V of the resistor. And we were told that delta V was 120 volts. Well, actually, that's not going to give me what I want, because I was asked to find the resistance. So I'm going to use this guy. So it's going to equal 120 squared over R. So R is going to be equal 120 squared divided by 1500 watts. So 120 squared divided by 1500 says the resistance is 9.6 ohms. Okay, so this is problem 7 at the end of the chapter. Not bad, right? capacitors, we need to think about resistors in combination. We can think about resistors in series, and we can think about resistors in parallel. So we know that in series, what is that? In series, it looked like that. Now, in series, the total voltage drop, the change in voltage equivalent, is the sum of the voltage drops over the resistors. So, you know, this would be delta V1, delta V2, delta V3. So the equivalent voltage drop is R equivalent, which is IR1 plus IR2 plus IR3. Okay? Since they all have the same current, we get R equivalent is just the sum of the resistors. So if this was a 10 ohm resistor, and this was a 20 ohm resistor, and this was a 50 ohm resistor, be 50 plus 20, that's 70, plus 10, that's 80. For this combination, it would be an 80 ohm resistor could replace all of those. So when they're in series, you just add the resistors up. No, resistors in series are like capacitors in parallel. Okay? When I have resistors in parallel, okay, so I have R1, R2, and R3. If I have a current coming in here, I1, you can think about it as being split up into an I2, an I3, and an I4. Okay, because since there is no resistance in this wire, this point, and this point are all the same. They're a single junction point. Okay? When resistors are in parallel like this, they all have the same voltage drop. Delta V is the same across all of them. So delta V over R equivalent is equal to delta V over R1 plus delta V over R2 plus delta V over R3 to get the current. Okay? And what it comes down to is 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. So if, for example, I had two resistors here, a 100 ohm resistor and a 500 ohm resistor, and they're in parallel, then 1 over R equivalent is going to be 1 over 500 ohms plus 1 over 100 ohms. So 500, 1 over, plus 100, 1 over. I have 1 over R equivalent is 0.012. So R equivalent is 1 over that, 83.3 ohms. Notice R equivalent is smaller than the smallest resistor that you have in parallel. Okay. Now, I want us to do an example problem where we have a more complicated we'll do, more complicated situation where we've got some resistors that are in parallel and some resistors that are in series. Okay, so let's look at a problem at the end of the chapter. We're going to look at problem, well, let's look at problem 25. Okay, now here's our circuit. We've got a 60 and a 40 ohm resistor that are in parallel. And then I've got a 60, 60, and 45 that are in parallel. And those two are in series with each other, and then they're in parallel with this 21 ohm resistor. So we're going to start breaking this down little by little. Okay, so let me kind of redraw this. So I've got a 60 ohm resistor here, a 40 ohm resistor here, and then I have 3 resistors here, 21 ohm resistor here. Okay, this is a 60 ohm, a 60 ohm, and a 45 ohm. So first thing I'm going to do is I'm going to eliminate this combination. So since those are in parallel with each other, I know that 1 over 60 plus 1 over 40 has to equal 1 over R equivalent. So R equivalent